going to give an example, study an application of stochastic geometry into wireless, and we will start with the performance of a mobile ad hoc network, or known as MANET. So, what is a MANET? We have a set of multiple transmitter receiver pairs, and the pairing is fixed. It means a transmitter is paired with a particular receiver only, and they are going to transmit and receive with one another only. So even if there is another receiver or a transmitter which can be close to this, it's only listening to this transmitter. Okay, and so communication between transmitter and receiver pair ups is random. Sometime it occurs and sometime it doesn't, but it's independent to the other pairs. That's why we call it ad hoc. And these pairs are fixed. A particular transmitter will always transmit to the paired receiver only, and they cannot connect to any other transmitter even if they are closer to it than the pair transmitter. And the example would be like a home Wi-Fi network. If you live in a colony and everyone has a Wi-Fi network, you can only connect to the Wi-Fi in your house. Even if you go outside and sometimes you are more close, sometimes you are closer to the neighbor's Wi-Fi access point, you cannot receive information from it, right? And in that case, that transmitter is going to interfere with your communication. So sometimes that is a bad thing to be close to the other transmitters. So what are the system models we are going to use here? We assume this multiple transmitter receiver pairs are spread over a two-dimensional space. The distance between each transmitter pair is fixed to be r, although the orientation is assumed to be randomly distributed independent to other pairs. Okay, so I'm just assuming R is fixed, but you can change R to be a random variable, and that is not going to change the calculation a lot. The math approach will be similar, although our orientation is assumed to be randomly distributed around the transmitter. So we assume that the location of transmitter is modeled as a homogeneous Poisson point process with density lambda. And for each transmitter, we assume the associated receiver is located at a r distance at angle which is uniformly distributed between 0 to 2 pi. And from displacement theorem, we know that the location of Rx is also a Poisson point process with the same density. Okay, because all the points are actually displaced to a location at r distance away. So they are going to follow a Poisson point process. So transmit process is xi, which is a ppv with density lambda, and the receiver process is x plus r theta I. This r theta I is the polar coordinates, and also it's also a ppv with density lambda. Okay, so we can see the location of receivers as a so if we only want to take one point process, first one, we can see the receiver process location as the mark of the transmitter location, right? So for each point we have transmitter at xi, and associate with it the location of the receiver is paired receiver. Okay, or you can just store the distance also. Okay, from that someone can calculate the actual location. So you can take r comma theta as a mark, or you can take xi plus r theta I, which is yi, as the mark of xi. And each transmitter, first we assume that each transmitter is transmitting at all the times with transmit power p. Okay, so the signal transmitted from the transmitter reaches the receiver via the wireless channel in between. And when electromagnetic wave propagates through media, the power of signal decreases with distance. Okay, so this is different than the wired one, that you do not worry about the geometry exact. But in wireless, the geometry plays a big role. As the distance increases, the power of the signal which is reaching at the receiver decreases. And this loss of the power actually depends on multiple factors. First one is the natural expansion of radio wavefront in the free space. Okay, so as you move away, the radio waves which are transmitting in all direction, it has a spherical wavefront and it increases. Because of this increase, the density of the power decreases. Okay, and then another is absorption loss. As you signal passes through the media, right, which is not transmitted to electromagnetic waves, the signal usually get so the different molecules interact with the millennium wave and absorb some of the power. And then we have diffraction losses whenever part of the radio front is obstructed by a opaque obstacle, and losses caused by other phenomena. Okay, so we are actually going to model the most important large-scale path loss, and that is because of the natural expansion of radio wave fronts in the free space. Okay, other effects can also be included, and many times they depends on what kind of frequency you are operating on. Okay, but we are targeting the generally the mobile frequencies around 700 to 1 gigahertz frequency, and in that case the most important path loss we see is the large case path loss, which is caused by the natural expansion of radio fronts. Okay, so let us understand this. Suppose transmitter has an isotropic antenna, and then you have a receiver of area A at distance D. Now, as the because the isotropic antenna electromagnetic waves is expanding in all direction. So if you construct a ball of radius d with center at transmitter location, then you will see that the this is the ball, and the receiver, because it at a distance d of area A, it will be just part of this ball. Okay, so I constructed this ball of the same radius as the distance of the receiver. So this receiver is just small part of the ball. And if you look at this complete ball, the electromagnetic wave is, because it is equidistant from the transmitter, the power of the EM wave is equally distributed around this sphere. Okay, and only this part of energy is being received by the receiver, and the rest energy, which is spread in other direction, will just further move away, right? And they will keep on progressing to other direction if there is no receiver there. So at distance d, the radiated power will get distributed uniformly in the sphere. So the power density would be transmit power divided by 4 pi d square. Okay, the area is 4 pi d square. So this is the density. So how many, and what is the quantity of energy which is absorbed by the receiver? That is given by the density into this area. So the power received by the receiver is equal to A into PT by 4 pi d square. Okay. And you can guess that as d increases, the power decreases, because this sphere will just keep on increasing, and A is going to be the same. Okay, so this gives us Fritz's equation, which says the received power is equal to transmit power into A upon 4 pi d square. Received power is inversely proportional to the square of transmit receiver distance. And more importantly, if you take this as some constant, which depends on area and other factors, this will be just some constant into d to power minus square. Okay, and this C is normally known as near field gain, and this minus 2, this 2 is known as the path loss exponent. Okay, and this we assume that there is no blockages or scatters between the transmitter and the receiver. Okay, so if there are scatterers and blockages in between, the signal power can further increase or decrease. So extension to other cases, when there are far more complex interactions, the path loss is generally modeled as C into d to the power minus alpha. C again is a near field gain, and minus alpha is known as the path loss exponent. Okay, and for free space, alpha is 2, and C was, as we see, is 8.4 pi. But for other environments, sometimes we can calculate and sometimes we just empirically fit it, which means we do some experimentation, the actual physical experimentation, by putting transmitter and receiver. We get some received data, and then we fit this model on this to compute the near field gain and the alpha on that. Okay, so this is a very simple pathless model, and but yet it is very popular, and it's a tractable model. Okay, other path loss model which people have used, which becomes important in the particular scenarios, is first one is truncated power law path model, in which we assume the path loss is given by the minimum of 1 into CD minus alpha. Okay, so if you notice this model particularly, what happens if D is very small, this can become more than 1, right? Which means if the, suppose you put D equal to very less, right? So then this becomes like 100. It means you are transmitting 1 watt and then you are getting 100 watt, right? Which is not correct. Right? So this is just a small problem in this path loss model. And if you are talking about dense scenarios where transmitter receiver can be very close, so in that case, this model is going to be create some problems. So people just use this so that they put a upper limit on the path loss, right? So if D is very small, we just cap it with 1. Okay. Another one which is to make for the same effect is dual slope path loss model. They say that the model we are talking about works only after some distance D naught, beyond D naught. That we know as the far field. In the field which is near the transmitter, EM wave works little bit differently and should be modeled using a different coefficient and the path loss exponent. Okay, so these all models and there are other models also which can be incorporated in the similar way. But in today in this application, we stick with the simple path loss model, LD equal to CD minus alpha. Okay, and then you can see how you can very easily extend to include these path loss models also. Okay, so gain in the signal power over distance is Lx. Path loss is actually known as 1 upon Lx. And hence, the received power from a transmitter located distance x at the receiver at origin is given as path gain into transmit power, which is Px into L of norm x. Okay, note that this basically depends only on the norm of x, not the orientation of x. Okay, and the path loss is experienced by all links including desired and interfering links. Okay, so that is the property of wireless propagation. So this will be in the desired also and the interfering links also. Okay, and then there are other factors which may affect the transmit power, such as the fading, which it may be random in nature, shadowing also. But for now we will just assume there is no fading, there is no other effect in the wireless propagation. Okay, now we denote the index of the selected pair by 0. Okay, so basically we are they were x1, x2, x3. We're just ordering it in a different way, which was we are saying that the receiver is at the origin and the desired transmitter is at x0. Okay, and because it's a stationary process, assuming the receiver is at the origin does not change anything. Okay, so the transmitter is at x0. This is the desired transmitter. I am focusing my analysis for this receiver actually. Okay, and this is selected typically arbitrary. So this will represent the uh, performance of all the links on the average. Okay, I haven't selected this in a particular way. It is just that I picked one receiver, made that origin, and then I look at a desired pair, and then the rest of the transmitter which are located at x1, x2, x3, they are all interfering transmitters, and their receiver is also located at r distance away at a certain angle. Okay, and here also you can notice the y distance between y0 and x0 is r because we have assumed the fixed distance, although the angle can be uniform. Okay, so since the interference is caused by the other transmitters only, you don't have to worry about other receivers where they are. Okay, so regardless of where the receivers are located, receiver location will have no effect. So we only have to worry about the transmitter process. And let us assume that each transmitter is transmitting with power PT. Okay, so now for the considered receiver y0, the desired signal power is given by this power which is received from the desired transmitter at x0. Okay, if I apply the path loss, the power from that transmitter is going to be pt into c into r to the power minus alpha. Okay, and r is the norm of x0. And for interfering power, if there is a transmitter at xi, the power from this will be C norm of xi minus alpha. This is a distance from the origin or the receiver into transmit power PT. Okay. So the total interference you have to add all the powers, and thus the total interference power will be just summation of the all the power, which is given by summation over all points excluding x0. Okay, so I'm not including x0 because x0 is my desired. Rest base station will contribute to, sorry, rest transmitter will compute to the interference. So this will be given as pt into seed norm of xi minus alpha. Okay, so I here interference is a function of x0 and the rest of the point process. X0 because we have to exclude that point, and phi minus x0 because this is a function of all point process without x0. Okay, so what will be my performance matrix here? I'm interested in performance of the magnet for a typical pair. Okay, so we just select arbitrary pair out of all pairs, right? Or we can just select a transmitter or a receiver arbitrarily. Okay, and in the typical pair, if the transmit send data to the receiver, what is the probability that the transmitter will be successful? That is the probability I am interested in. Okay, and this is the average performance over the whole network. And when we call a transmission to be success, we assume that for transmission to be successful, the assigner of that transmission link should be greater than some threshold. Let's assume 5 dB. Okay. So if I take the assigner divided by the interference plus noise, if that ratio is more than 5 dB, then I say the transmission is successful. Okay. And that is typically the case that a transmission success depends on the assigner threshold. So the probability of success will be given as the probability that the assigner of a typical receiver is more than threshold. And this we also know as the transmission success probability given the threshold time. So that will be our prime focus first. We will compute this in terms of the density and the distance r. So first we will focus on interference characterization. Distribution, so we have explicitly said what is I in terms of function x0 and the point process without x0. And we are interested in characterizing the distribution of this random variable I. So how can we compute, how can we characterize interference or any random variable? We can just compute a Laplace transform. And we know that Laplace transform uniquely characterizes a random variable. By looking at distribution as Laplace transform form, we can uniquely determine the distribution of that random variable. So Laplace transform would be given as u to power minus si. Okay. And here too, before computing the interference, I'm going to condition on the desired transmitter. Okay. Because without a desired transmitter, I cannot define the interference. Okay. So once you have the receive pair and then you have a desired transmitter, then we know that the rest of the base station transmitters are the interfering ones. Okay. So this interference is always conditioned on the desired transmitter. So this I am conditioning that the x0, which is a desired transmitter, is the part of point process. Condition on that, the interference Laplace transform is given as u to power minus si given x0 belongs to phi. Okay, and then I am explicitly writing that I is a function of x0 and phi minus x0. Okay, and sometimes people just represent shorter way. If they instead of they can use the palm probability notation, and instead of writing this conditioning, they just say expectation with respect to phi condition on a point x0 is of exponential minus si. Okay, and this we know that this superscript represent the palm probability, which means there is a this expectation is computed with the condition that there is a point at x0 in phi. Right. So recall that the transmitter process is a Poisson point process, and we are conditioning on a point at x0. Okay, but from Slivenac theorem we know that the condition on the point x0, the rest of the pp still looks like a Poisson point process with the same density. Okay, so distribution of sum of received power from all the base stations excluding the base station or the transmitter at x0, condition on the point x0 is same as the distribution of the sum of the received power from all base stations from an unconditional Poisson point process. Okay, so you can just say that instead of this, if I remove this conditioning and remove this point and just compute expectation of phi exponential minus si x0 comma phi, that will be the give you the same distribution. Okay, so if I either I condition on the point and I'm looking at the some function which is uh, a function of all point process excluding that point, or I can just look at the unconditional point process, then there is no point at x0, so I don't have to remove or add that point. Okay, so this just means that if I take an independent unconditional Poisson point process phi2 with the same density and define I2 as summation over all points of phi2 pt into lxi, which is the transmit summation of the transmit receive power from all transmitters, from an unconditional independent Poisson point process with the same density, then I and I2 are same in the distribution. So I can just compute the Laplace transform of this I2 and I will get the distribution of the original I. Okay, and because the distribution is same, it means the Laplace transform of I and I2 are going to be same, and also this means all the moments are also going to be same, right? So it means the mean of I is same as the mean of I2, and in the palm notation I can just write this as E expectation of x0 of I, which is a function of x0, and phi minus x0 is same as E of I2. Okay. So first I'm going to put my focus on the mean of the interference. Okay, so I will first compute what is the mean of this interference. Okay, so then I will compute the Laplace transform. So the mean, which is given by EX0I, is same as E of I2, and there is no conditioning here, note that. And I2 is summation over all points of transmit power, field gain, and the normal distance of minus alpha. Okay, and note that this is nothing but just the summation of some function over all points. I can apply Campbell theorem, and this will just give me lambda ptc in integration of norm of xi, norm of x minus alpha dx. Okay, note that we denote capital X here because these are random points, while these are deterministic integration, so x is small. Also, there is j here because there are many points, and here there is no j because that number of points is already weighted by lambda. Lambda into dx denotes the number of points at the location x, and they all points have the same function, norm of x minus alpha. To further solve it, I can use the polar coordinate because this is a function that depends on distance. So if I use the polar coordinate, norm of x becomes r, dx becomes r dr d theta, and the integration becomes from 0 to infinity for r and 0 to 2 pi for d theta. And this is not a function of theta, so this will just become 2 pi, and this will become r minus alpha plus 1 dr. Yeah, and then there is a lambda PTC, and this can be solved, but to know that I need to know the value of alpha actually, right? Because if alpha is high, then this will be negative coefficient. If alpha is more, it will be positive coefficient. If alpha is 1, right, this will be just 0, right? So it actually depends on the alpha. So let's take one case, alpha is more than 2. If alpha is more than 2, then this refers to scenario when the path loss is larger than the free space path loss. Okay, it means there are more scatters than the free space and the path loss is decaying very fast. Okay, so this alpha actually shows how fast the power is decreasing with distance. If alpha is high, the path loss decreases very fast. If alpha is low, the path loss decreases slowly. So alpha greater than 2 means the path is decreasing very fast. It means there are many scatterers and a lot of obstacles in the environment. Okay, So interference decreases more sharply with distance than expected in the free space pathless. And if I compute for this, because alpha is more than 2, minus alpha plus 1 is going to be positive, and this will give you minus alpha plus 2 divided by minus alpha plus 2. Okay, and this is positive. So yeah, so once I get this, I can notice that because alpha is more than 2, this is a negative term. So for to write in the positive coefficient, I will just will be 1 upon r minus alpha minus 2. And if I put infinity, this will be 1 upon infinity, which is 0. And if I put 0, it will be 1 upon infinity, which is going to be infinity. So that is going to give me to overall infinity interference. Okay, and so you look at this, uh, the infinity shows the points transmitted located at the infinite distance, and the 0 limits correspond to the transmitted located at a very close distance. Okay, so the points which are very far away, that are not a problem, that are just contributing 0. Okay, but these points which are located at the origin or nearby are making the whole interference infinite. Okay, so this means because interference is decaying very fast, the point which are outside very far away, that are not changing the interference by a huge amount, but the point which are close by, the signal power is so much that the interference is actually becoming infinite because of that. Similarly, if I take the second case, when alpha is less than 2, so in that case, once I solve this, I get minus alpha plus 2. And because alpha is less than 2, this coefficient is negative. Sorry, this is positive. So when I put infinity, this will be infinity to the power positive coefficient, that will become infinite. And when I put 0, that will become 0. So in that case also the interference become infinite. And the problem here is because of this infinite limit, right? So this tells the points which are close by are not a problem, but points which are very far away, that are contributing infinity. Okay, and it means the because alpha is less than 2, the interference is decreasing slowly with distance. It means that the decrease is so slow that the points which are very far away are contributing infinite interference to it. So in this case, the problem is occurring because of the transmitters at very far away. Okay. Note that even if the signal power is decreasing, the number of transmitters are growing, right? As you move away from the origin, right? Because if you create a ring, so if you look at how many base stations are, how transmitters are there with a distance d, right? So you take a ring of radius d and a small area delta d. The number of transmitters in that area is 2 pi d into delta d. Okay, and so the number of points in this ring is increasing as you increase the radius of this ring. So at infinite radius, right, if you take a ball of d and ask how many points are there outside this, so there are infinite number of points at the infinity. Okay, and if they are contributing very small, if their interference is not decreasing fast enough, they will contribute to a infinite amount eventually. So, and now if I take the last case alpha equal to 2, in that case, this will be just r to the power minus 1 dr. So this will be become log r. So in that case also 0 and infinity, if you put log 0, that is also minus infinity, and log infinity is also infinity. So both terms will contribute to infinity. So in that case, or the base station which are close by and the far away, both are contributing infinity. So the mean interference is always infinite. It's respective of the value of the pathless exponent. Okay. However, when I say these are all infinite, still they are different. These cases are different, and we will see that the reason of I being infinite is different for each case, and because of that, the distribution of I would be different in these three cases. To understand the behavior of mean of interference for these three cases, let us look at the behavior of t to the power minus alpha. So behavior of delta minus alpha with D decreases. This both of them decreases regardless of alpha. But if alpha is high, like 4, then the decrease is very fast. Okay, and for alpha lower values, the decrease is slower with the distance t. Okay, so if you look at this, lambda dx is the average number of points in the area dx, and lambda dx norm of x minus alpha denotes the contribution of points in the interference located at the area dx. Okay, so I'm not including pt and c, but you can just add them also. They are just constant. So if you include pt and c also, they is the exact contribution of these points in the interference. Okay, but if you just look at the scale behavior, let's ignore it for now. So lambda dx norm of x minus alpha kind of shows the contribution of points located in the area dx. Now this function is radically symmetric. So you can just take a small ring with radius r and width dr, and all of them will have the same contribution. So the total contribution from this ring would be norm of x minus alpha, which is r to the power minus alpha, into lambda into, and the area is 2 pi r dr. So total will be 2 pi r dr into r to the power minus alpha, which is given as 2 pi r minus alpha plus 1 dr. So this is the contribution from the ring of radius r. And you have these many rings, you add them all to get the total interference. Okay, so let us see how does this contribution grows, right? As I take more and more, as I increase the ring size. Okay, so at a smaller, so these are the area of this is the value which is shows the contribution of the transmitters located at 6 distance away at a large distance, and these are the contribution of the transmitter which are located at a small distance. Okay, so what I'm comparing is to alpha. So when alpha is 4, then you can see the transmitter which are far away are contributing very less, right? But for lower alpha, the contribution is larger. On the other hand, at the smaller radius, the contribution of the transmitter at a higher path loss is more than the contribution from the transmitters of the lower alpha, right? And what is the case here? It just shows because the interference is decreasing fast, so the contribution is low even if you have more base station, right? So you are seeing this factor 2 pi r dr. It is showing that as r increase, there are more and more base station in the ring, right? If you take a larger ring of larger radius, then its area actually decreases with as r. So there are no more transmitter in the ring of larger radius, but because the transmitter power is the interference power is decreasing with alpha significantly, the total contribution is small, right? Here you see the opposite effect because of this path loss, which grows as r becomes smaller. Okay, so here the base stations transmitters are small in number, but their individual power is high, right? So because of that, uh, as alpha increases, the transmit power increases for lower, the receive power increases with lower. Okay, so in case 1, alpha greater than 2, mi is infinite, not because of the transmitter which are far away, but because of transmitter which are close by. So because of this, mi is infinite because of the value of the indefinite integral at x equal to 0, not because of its value at x equal to infinity. Okay, so boundedness of interference is due to the base station located close to the origin. Okay, so their number is finite. If you take a ball of epsilon, their number is finite, but the interference from them is very large, such that the total contribution is not finite. Okay, so this tells that, let's just assume a small ball of radius epsilon, ball of 0 epsilon at the origin. Number of transmitters which are in this ball is lambda pi epsilon square. Okay, and this function values goes to infinity, right? the base station transmit power from this transmitter in this area for each individual transmitter is R to the power minus alpha. And as epsilon is very small, this goes to infinity. Okay. The total contribution from this point is more than lambda pi epsilon square into E minus alpha. So E minus alpha is the value and lambda pi square is the average number of transmitters from this point. So this is lambda pi epsilon minus lambda pi epsilon to power minus alpha plus 2, which also goes to infinity as epsilon goes to 0. Okay, so this is the region why for this case the interface is infinite, right? So number of transmitters are finite, very small, but each individual contribution is very large. So when you multiply them, because alpha is more than 2, this coefficient becomes positive, right? Alpha minus 2 become positive. So this whole contribution goes to infinity. Okay, but note that there is there may be cases when there is no base station in this ball, right? You take epsilon ball. What is the probability that there is no point in this ball? That is a finite probability, e to power minus lambda pi epsilon square. Okay, so with that probability, there is no point inside this. So the contribution is still bounded, and in that case, you can compute that the interference, total interference is beyond, not infinity, is beyond some limit. Okay, sorry, it's below some limit. So with some probability, you can compute. So the probability that there is no point in the ball of radius 2, that is e to power minus lambda pi 2 square. With that probability, there is no, the interference is bounded by some finite amount. Okay, and eventually this is the artifact of the path loss model we took, because we are assuming that the path loss can go to infinity as we go very near to transmitter, which is not exactly the case. In reality, the path gain is always bounded, right? You cannot get more than the power which is transmitted. So if you include that factor, maybe you will get the finite interference. Okay. Now in the second case, when mi is in alpha is less than 2, mi is infinite because of the value of the indefinite integral at x equal to infinity. Right. In that case, the nearby points are fine because the path loss is not increasing that much. You can apply the same calculation here. When alpha is less than 2, this becomes positive. So the total contribution becomes goes to 0 as epsilon goes to 0. Right. But here the problem is coming because of the transmitters located far away. Okay. So if you consider a circle of radius epsilon and count all points outside it, the number of points are infinite. And if LR does not decrease with a certain rate with distance, total contribution of interference from the points outside this ball, which we term as far, is infinite. Okay. So note that the infinite mean doesn't necessarily mean the distribution is not defined. In the first case, there is finite probability that there are no point inside this ball of radius epsilon, right? So with that probability, interference is finite. So you can still compute the distribution of interference condition on these events. However, in the case second, the interference is always infinite, right? Right, there is no probability that interference will be finite, because if you try to compute the probability that there is no point outside this ball of radius r, that is going to be 0 because there is an infinite area outside this ball, right? So if you try to compute the void probability, it will come out to be 0. So there is no small probability, even not a small probability, that there is no point outside it. In fact, there are always going to be infinite number of points outside it, and with that the interference is always infinite. And in that case, the probability density function and the Laplace transform of this interference is not defined. So let us understand the difference of the interference distribution for these two cases. For alpha greater than 2, interference is also infinite due to singularity at the origin. Okay, path loss is unbounded at the origin, and that is the reason for this interference to be infinite. And for alpha less than 2, is infinite due to unbounded number of interference located at far distance, whose path loss doesn't decrease sufficiently fast enough to make some interference vanish at infinite distance. Okay. In this case, it is almost surely finite. You can show that it's almost surely finite as the following condition is satisfied. Okay. So if you look at uh, the existence of the Laplace transform of some function, this satisfies this property. So this means the Laplace transform should exist. In this case, this is not true. So it is infinite and its Laplace transform does not increase. Okay. So it is clear that we can avoid interference to become infinite by taking alpha greater than 2 and using bounded pathless model. So that is one way you can also use, and that is more realistic models to show that interference is not infinite in this case. But there is no way you can do for this case. Now compute the Laplace transform of the interference. So remember we have shown that the interference has the same distribution as I2. So we'll compute the Laplace transform of I2, which will be same as Laplace transform of the actual interference. So recall that I2 is given as the summation over all points of I2 transmit power multiplied by the path loss. So the Laplace transform is given as e to power minus SI2's expectation. So if I put the value of I2 here, what I get is the expectation of exponential of minus S sigma Pt Lxi. So if you treat S into P2 into Lxi as a function fxi, then this is expectation of exponential summation over fxi. Okay, and then that you can see as a Laplace functional. So because it's the expectation of exponential of summation of functions over all points, so I can apply the Laplace functional of the PPP, which will give me exponential minus lambda integration of 1 minus e to power minus spt lx dx. Now since I will put back the value of path loss here, this will give me exponential minus lambda integration of 1 minus e to power minus scpt norm of x minus alpha dx. Okay, so this is the expression we got, and we have to now solve this integration to further compute the Laplace transform. So if we focus on this, we notice that this is a form of this only depends on the distance norm of x. So I can use polar coordinates. So when I put x instead of x, I put r d theta. This will become r dr d theta, and d theta it's not a function of theta, so that will become 2 pi. And this will become 1 minus e to power minus scpt, and this will become r to power minus alpha. Okay, so first we will just solve this integration, and then we will compute the rest of the Laplace transform. So this integration is, if we focus on, this is 1 minus e to power minus scpt r minus alpha r dr. So now if you look at the behavior of this, first let us understand whether this integration exists or not. So if you look at the behavior of gamma minus alpha, then it is infinity at gamma equal to 0 and 0 at gamma equal to infinity. So it goes from infinity to 0 as gamma goes from 0 to infinity. So this means e to power minus s some s coefficient gamma minus alpha will become 0 at gamma 0 and 1 at gamma equal to infinity. So 1 minus this term is 1 at gamma equal to 0, and then it decreases to gamma equal to infinity. So this function is always bound between 0 to 1, so it doesn't take very high value irrespective of the value at alpha. So near the origin, when gamma is very small, 1 minus e to the power minus gamma minus alpha is always bounded by 1, irrespective of the value of alpha. So since this region near 0 is bounded, the contribution of a bounded function from this small region is bounded. So if you take a small s and you integrate a function fx dx, and this will be less than if you integrate the maximum of fx over this region. And if the maximum is bounded, then this is also bounded. So the contribution from points nearby is not a problem. So behavior near the origin is not a problem because it is bounded, and the region around origin is of course small. So if you have a bounded function in a small region, the contribution is limited. So the problem actually would come if this integration does not converge, can be due to its behavior at the infinity. So if this function does not decrease to zero fast enough, then it may happen that the integration will just goes to infinity. Okay, so that it is important that the behavior at the infinity uh, uh, at this function should decrease fast enough so that the integration is bounded. Okay, so you can notice that mainly if alpha is more than 2, then this will function will convert decrease to 0 with sufficient rate. And if alpha is less than 2, then this function will not converge. So although for both cases the mean interference was infinite, when we try to compute a Laplace transform, it is different. For alpha greater than 2, the integration will be defined, while for alpha less than 2, this integration will become infinity, so Laplace transform will not be defined. So let us look back to this integration once again. And to further solve it, I will first try to get rid of all this coefficient. So I will do a substitution. SCPT r minus alpha is equal to t minus alpha. And because of that, dr would be this thing. And once you solve it, all this coefficient will come outside, and you will have 1 minus e to the power minus t alpha dt dt. So this is just a function of alpha. It is no longer a function of any other parameter, and all the other parameters will be in the form of SCPT to power 2 by alpha. So rest is just to solve this. Let us see how do we solve this integration. If I first consider the indefinite integral, this form, then I will just apply by parts. So this will be my first part, and second part, this will become 1 minus e power minus t minus alpha integration of t dt minus, and then derivative of this term t dt. Okay, so this will become 1 minus e to the power minus t minus alpha t square by 2, and then this will become this term. Now I will apply limit from 0 to infinity to these two terms. In the first term, I have to apply limit at infinity because one term is going to infinity and the other term is going to 0. So if I apply both, I will get a term here, limit t tends to infinity, t to minus alpha. And this term will nicely integrate to this term. Okay. To further solve this, I will put a substitution u equal to t minus alpha, and I will get this form, which is in the form of a gamma function. Okay, so once I put this back, I will get this function. Okay, so now I can notice that this part is particularly, this will converge when the coefficient is more than minus 1. Okay, so 1 minus 2 by alpha is greater than 0, then this integration will converge, which is the equivalent condition that alpha is more than 2. And if alpha is less than 2, this will not converge. So what I get is this, and then this will converge to this value, gamma 1 minus 2 by alpha and half, where gamma is the gamma function defined in the following form. Okay, so this you can numerically calculate, and you can always notice if z is a integer, then this just becomes the factorial. And the second part also, this part, this will also converge to 0 if alpha is more than 2. If alpha is less than 2, then this will become infinity. Okay, so so if I put this term back into the original expression of Laplace transform, I get this one. So what I get is, if alpha is more than 2, the Laplace transform is exponential minus lambda pt2 by alpha, s2 by alpha, c2 by alpha, gamma 1 minus 2 by alpha. And if alpha is less than 2, then this is just 0, which means the Laplace transform does not exist. In this case, the interference is always 1. So we have seen that even the mean is same in both cases. There is a difference between the distribution of I. For one case, it does distribution exist. For a second case, distribution does not exist. Now we will proceed to assigner coverage. We now know the Laplace transform of the interference. From that, we will compute the assigner coverage. So recall that the assigner coverage is given as the probability that the assigner is above some threshold P. Okay, an assigner of a typical pair. So we have calculated the assigner formula, which was the solving power divided by noise plus interference. And the solving power is PTC R minus alpha, because the distance between transmitter and the desired receiver is always R. Then n, and the I we have seen, and I or the I2 has the same distribution. So I can replace them and greater than tau. So now I will put this here. This will become PT CR minus alpha is greater than n plus I, and then you have a tau also there. Okay, so this is deterministic. This is deterministic. Only thing is remaining is I. That is where you have a probability. So this is equivalent to saying probability that I is less than PT C tau minus alpha R minus alpha minus n. Okay, so now if we know the CDF of I, this is nothing but the CDF of I calculated at this point. So this is CDF of I calculated at PTCR minus alpha tau minus 1 minus n minus noise. Okay, so what we need now is the CDF of the interference. Okay, we have the CDF of the Laplace, we know the Laplace transform of interference, but from that we need to calculate the CDF. So there is a lemma which we can use, is known as Gill-Pallas lemma, which relates the Laplace transform and the CDF. So it's kind of inversion of the Laplace transform. So it says if I is a random variable with Laplace transform this, then its CDF is given as 1 minus 2 minus 1 upon pi integration of 1 upon 2 imaginary part of e to power minus jts into Laplace transform evaluated minus jt dt. Okay, so if I put this back into the original expression and replace s with this, what I get is 1 minus 2 pi 1 minus 2 minus 1 upon pi integration of this term dt. Okay, now it is an imaginary part, so I can, this is an exponential part, so I can extract the imaginary and the real part from this. So what you get is first I'll do a substitution, t pt cr minus alpha tau minus alpha equal to y, and which can help me collect sub coefficient back, and I get this particular form. Okay, so right, so there is only the transmit power and the R in this term, in the noise term. Rest there is these terms are independent of that. Now we know that j to power 2 by minus j to power 2 by alpha is cos pi by alpha minus j sin pi by alpha. Okay, so if I put this term back into this and extract these two terms together separately, what I get is 1 minus 2 minus 1 upon pi integration of 1 upon pi exponential of this term. This term is the amplitude part, so it just comes out of the imaginary part, and then you have sine of this term dy. Okay, so if I look at this, this is actually a very complicated expression, and it can only be numerically calculated. It may not be possible to solve it further. You can of course have a special case when the noise is 0. You can put that. So expression can be a little bit simpler, but still it is hard to complicate. It's very complicated expression and hard to solve. So what I do is I make a simple approximation here. Let's just take the interference from the dominant interference, right? So what is dominant interference? It is, there are many interference around you. You just take the closest interferer and compute the interference from it. Okay, so this will of course give you a lower bound on the interference, so it will give you an upper bound on the performance, right? You will get a performance which is better than what in reality is, but it can give me some simpler expression. So that x1 denote the location of the closest transmitter, and we know that the interferers are also form a unconditional PPP, right? So condition on the typical pair, the rest of the point process which are interferer also form a PPP. So what is the distribution of the distance of x1 that we have already calculated? This is the distribution of the distance of the closest point of a PBT. Okay, so interference from that is given as PTLX1, right? So if I ignore all the other interference and only have this interference, then I can calculate CDF, right? CDF is given as I less than x equal to PTC norm of x1 minus alpha less than x. This will mean that if the interference is less than s, it means the nearest the point should be at this much distance. So this is same as probability x1 is more than this value. Okay, and we know that probability x1 is more than r. That is the void probability that the x1 does not lie in the ball of 0 r. That is given as e to power minus lambda pi r square. So if I put r value here, I will get e to power minus lambda pi as cp divided by p s by cpt to power minus 1 upon alpha square. So this is the CDF of interference. So once I put in the assigner coverage probability expression, which is CDF of I evaluated at this, and I put the CDF expression back, I get this expression. Okay, so, and of course this is the case when this is more than 0. If this is less than 0, then the CDF of I is just 0. So probability, if the noise is so much that even the in absence of the interference, the desired signal server based transmitter cannot provide enough coverage, then the probability of assigned coverage will always be 0, regardless of the interference. But if the noise is less, then this limit serving power, then you can compute this. Okay, and of course you can take noise equal to 0. So you again get a much more simpler expression, which is just e to power minus lambda pi r square tau. Okay, this acts as an upper bound to the actual coverage performance. So still that was with the normal path loss model, and now I will quickly cover how you can change this path loss models. Right? You saw that there was issue with the normal power path loss model when the density is very when you go to near the transmitter. So let us look at that. So in the analysis, the path loss function was taken as this particular format, and as x goes to infinity, this path loss goes to infinity, which may mean that the receive power, which is transmit power into this, can be infinite or can be higher than the transmit power, right? Consider this example. Let the transmit power be 1 watt, C equal to 1 and R equal to 0.5 meters. Then for alpha equal to 3, the receive power will come out to be transmit power multiplied by 0.5 to power minus alpha, which will be 8 watt. So if you're transmitting 1 watt, you cannot receive 8 watt anywhere. Right. So this behavior is not practical, and it is caused by the incorrect modeling of the near field behavior. So this path loss function works fine for all the practical distances, right? When the transmitter receiver are far away, but when it comes close, this does not correctly model this, right? And because the expression does not understand this, so when you try to apply this in analysis, sometimes you can see a very bad effect, such as the mean interference going to infinity, even for alpha greater than 2. So how can we use different path loss models? So people have used other types of path loss models also. One example would be we would just upper bound the path loss to 1, saying that at the far distances, when this value is less than 1, the path loss is this, but as you come closer, the path loss cannot be more than 1. Or you can have this kind of 1 upon x power alpha. This has a similar effect. It doesn't let the path loss becomes more than 1. Okay, so these two ensures that the receive power cannot be more than transmit power. And there are other different path loss models also, dual slope path loss models and exponential path loss models, which are there. But I will just focus on one of these two to just show that how you can apply this to the analysis and compute for them also. So let us see the mean interference, how the new path loss model will change the mean interference. So recall that mean interference is given by expectation of summation of interference, which is transmit power into path loss and summation of that evaluated over all points. So now if the path loss is minimum of 1 comma r minus alpha. I'll just put that. Again, is a polar, I can use radial polar coordinates because this is just depends on the norm. So I get nice 2 pi lambda pt and then integration of 0 to infinity, the path loss r dr. So the path loss, if I put it, will become 1 r minus alpha. So I can break this integration into two parts, right? When r is less than 1, this r minus alpha is less than 1, so it will is more than 1, so this will become 1. And if r is greater than 1, then this is less than 1, so the minimum would be r minus alpha. So this is why I've written this, and then we can further compute it very easily. This is r square by 2, and this is this term. And so finally I get this expression. And here you can notice that if alpha more than 2, then this is finite. The interference is finite because I have, so recall that in alpha greater than 2, the problem was coming because of the interference very near to the receiver, right? And because of that, the interference was just blowing up. Here I have avoided that fact by upper bounding the path loss. So because of that, I get it a finite value. Right, and interference at the far point was not a problem. But now if I put alpha less than 2, you see it is still infinite because the problem was not because of the points close by, the problem was because of the behavior at the infinity. There was many base stations which are contributing non-zero values leading to an infinite interference. And that has not changed here. So I have only modified the behavior near the origin. So some interference in this case is also infinite. So this means for alpha less than 2, the mean is inherently infinite, and the sum interference from power transmitter is unbounded.